Hi, in this video, we want to talk about model validation. All right, so remember, when we are building our supervised learning model, we have our training data, we have our validation data, and we have our test data. Well, we build our model on the training data, we do parameter tuning and select our best model using the validation data, then we get an honest estimate off of the test data. Well, it works out. We have multiple ways to decide which observation goes into train, which observation goes into validation, and which validations go, or which observations go into test. And so we're going to just talk about options that we have in different situations. And we'll also talk about situations where I don't have as much data as I would like to have. And so we might actually skip the validation, or we might just go completely with trained data because I have such light data, or possibly imbalanced data where I have special data that I just have such little data of, so few observations, that I need to do some things that kind of go against best practices. All right, so one thing is, the reason why we go through this paradigm of splitting our data and evaluating is that we want to make sure that our model generalizes to unseen data. We want to make sure that our model is able to make predictions for the future upcoming data that we haven't seen, not the data that we have seen. And that's why we do this train validation test split. And so, our goal is to build the best model possible, whether that's for inference or for prediction or a balance of the two, or possibly for controlling a system, based off of the data that I have, not the data that I'm going to see. All right, so our training data is the data that we're going to actually build our model on. And you'll hear people say building a model or fitting a model is training the model. Yeah, I prefer to not use the word training for the purpose of fitting a model, because it's there's multiple usage of the word train in the same lane. And so when I personally say the word train or training, I'm referring to the data set itself most of the time. All right. All right, so let's go ahead and run through some examples of some stuff. So I'm setting up my workspace. I'm suppressing the number of digits printed, avoiding scientific notation, suppressing warnings that I don't care about, clearing my workspace from any artifacts, and I'm going to be using piping from the tidyverse in R. Now I'm going to be using the Kaggle house prices data set for this video. And this is my prepared version of that data. In a previous video, I did all my data prep. All right, so I'm going to break up my data into training, validation, and test sets on this. So this is how you could do it, do this holdout set approach using tidyverse. And so here, I personally made the decision that I wanted I wanted to have I want to have a third training, a third validation, a third test. This is putting a lot of data into validation and to test compared to other standards. Typically, you'll see around 70% will be in the training data. If you have a good amount of data, it honestly doesn't really matter that much what the proportion is. So if I have a lot of data, I'll tend to put less into training just so that my model building is faster, because that's a step that's going to take a while. And here I just picked 1/3, 1/3, 1/3, just to make it easier to understand. A typical split will be something like maybe 70, 15, 15. And the less data I have, the more data, more proportionately is going into train. All right, so here, how I'm doing this is that if it's greater, I'm doing a random number generation, uniform, standard uniform. If it's greater than 2/3, then it's going to be a train data. Now, when the random number generation is between 0 and 2/3, less than 2/3, then I'm going to do another random number generation, and I'm going to have 50-50 of validation or test. And so 2/3 of the data are going to end up in this if-else statement, and half of those are going to be validation or test. There's several different ways that you could have done that. You could do this. This is just how I picked it. I didn't feel like storing the random number anywhere, and so I just did a random number generation a second time. Now, here are the predictor variables that I'm going to use in my model. And so in the previous video, I talked about feature selection. This is my long list of features that I will consider. There are a few of these that I could get rid of that would probably improve the model if I got rid of them. I'm going to handle that on another time. Now, I'm going to go ahead and rescale my data. So when I do this type of data prep, I need to center and scale for a lot of different types of models. And remember to record the mean and standard deviation, or what you subtract and divide by if you're going to be rescaling your data. And I'm not going to use the mushroom data set on this one. I just copied and pasted the code. All right, so the training data, very clear, very obvious. The classic approach in predictive analytics is coming from statistics, and classically we only had training data. Remember that back in the day, data, we didn't have a whole lot of data, and the idea of partitioning your data for accuracy checks wasn't even on anybody's radar till pretty late. And so if you look at like a classic regression course, they really don't talk about validation and test data at all. Everything is just your training data, and you work on that. Now, remember that if I check my accuracy on my training data, the data I use to fit the model, my statistics are going to be optimistic because the model is fine-tuned to the data that it sees. And so we have to watch out that my model is fine-tuned on the data it sees, but the data it sees is not the data that I need to make predictions on. And because I need to make predictions on things I haven't seen yet, right? And so there's always a difference. And we don't want to overfit. We don't want to put too much emphasis on that data. All right, so we're going to have the validation and test split. Now, the validation data, what I'm going to do is I'm going to first take my test data, sorry, my trained data. I'm going to take my trained data, I'm going to fit my models, a whole bunch of them, and then I'm going to check to see which of these 20 different models is the best one to work with. All right, so then I'm going to take my validation data, I'm going to drop my validation data into the models I just fit, and I'm going to check to see, hey, which one is the most accurate? Whichever one is the most accurate, that's going to be the one that I choose. Now, there's a downside to this. When I do the validation data, it could just be that just by happenstance, the combination of my data and my validation data and the model just happened to look really, really good, and just by happenstance. And so my validation statistics tend to be on the optimistic side. And so if it's optimistic, I need to know how is my model going to perform in the future. That's my number one goal. Remember, I don't care about the data I have. I care about the data I'm going to make predictions on. And so I need to simulate the prediction process. And so the test set, after I've done my validation and I've selected my best model, I'm going to walk up, I'm going to take the test data into my best model, I'm going to drop the test data into my best validation model, and then I'm going to check my statistics. And that's going to be my honest estimate of what's going on. So this way, my training data statistics are going to be optimistic by a lot. Validation test statistics tend to be a little bit optimistic. Remember, I'm picking the best, which means that there could be like a luck aspect that makes that one model look better than it really is. And then the test gives me that honest estimates. All right, so we have optimistic results when I use my training data. So if I was to take my model and I put my training data into the model and I evaluate its accuracy, the results I'm going to get are going to be optimistic compared to what's going to happen in reality down the road. And so, we don't want to trust it. Now, we are still going to do this computation, knowing that's optimistic, and check the difference between my training statistics and my validation statistics, difference between my training statistics and my test statistics. If I have a large gap, that's an indication that I have overfitting. Now, my validation data, it can be optimistic also, especially if I built a lot of models. Let's say, hypothetically, I built 1,000 models and I wanted to check to see which of those is best. Well, I'm going to use my validation data. I'm on all 1,000 models, and I'm going to check the accuracy of all 1,000 of those models on the validation data. Well, 1,000 opportunities for luck to kick in and a particular model to look better than it really is. And so the more models I build, the more optimistic I should expect my validation statistics to be. And so validation data is not enough if I have sufficient data. And so then what I'm going to do is, after I've picked my model, then I'm going to put my test data into my best validation model and then check to see, hey, what is an honest estimate of performance? Now, remember, time is going to pass between when I built my model and my actual prediction data is generated when it lands in my lab. And it can end up that things happen in that time span. So let's say that I build a model today and I'm going to put it into production, and there might be like a pilot phase. That's typical for a lot of large dollar projects. Is that you don't just take a model and slap it in and run with it. You let it, have a trial phase. All right, so a trial phase happens, and then you go and you start actually using the model. Well, remember, I'm using old data for my training data. So, like, let's say that my training data is from the past 2 years, and I build it today. So that I've got data that's 2 years old in this model. I go through my pilot phase, and so that that's an additional quarter. Then I actually go into production, and so things can change from that previous the previous years to the actual the data that I'm making predictions on. And so there can become changes in the target predictor relationship. And so what will happen is that my model will be predicting as if things were the same way they were in the past. And also, I have a change in the distribution. So, let's say that fraud, you have a model for fraudulent activity. Maybe fraudulent activity goes down, fraudulent activity goes up. My model is still going to be behaving like it was in the past. And hopefully my model will actually detect those differences. We could have changes in our target variable. We could have changes in our response or in our predictor variables. And so that will change the distribution of what I observe coming out. So if I was to go and take my predicted values and take the values I had on my training validation test data, I can see that there'll be a difference. That's one of the things that we're going to do to check to make sure that things are coherent. When every time I run my model to make a prediction, I'll compare the predicted values to like my benchmark data set. And there might be a difference. That difference may be correct, it may not. We won't know until it's too late. But we definitely want to know if there's a difference from our benchmark data. And so we need to be ready for changes in the distributions. All right, so now sometime you're going to find yourself in a situation with too little data for your project, and that's going to happen. And your job is to build models. Your job isn't to whine about how, what best practices are. We need to get the job done, and we need to make sure our stakeholders are happy. So some alternatives that we have, we can use training data only. So here, what we're going to do is, I have such little data that I just say everything's in my training data. I don't have validation. I don't have tests. I'm going to use my training statistics to show me what's going on, but I know it's optimistic. I know that the accuracy on my training data is going to be better than what I can anticipate. If it's good, if I feel confident, I can proceed. This is an option that we have. Another option is to do a train test split. So here, I'm going to use my test set as my validation and my test data. And so I'm going to use my test data to select my best model and to give me my estimate of how things will perform in the future. This is a better choice when I only build a few models. If, let's say, I only build 2 models instead of like that 1,000 I mentioned earlier, well, only building 2 models, I'm not really exposing myself to luck, like kicking in to making a model look better than it really would be. And so I'd probably be okay with just doing a test set instead of validation. Now, here is something that's controversial in the data science community, and this is to refit your model after validation or test. Okay, so what I've talked about so far is I build my model on the training data, and then that is the model that goes straight into production. Another alternative that I have is that after I build my model initially, and I select my model and I do my test set, I could go and let's say I take all my data and I retrain my entire model on the entire data set. All right, well, this has the advantage that I'm using the entire data set in the training data. Really, if you think about it, you want the best data you can have in your training data. Your training data is what actually impacts those predictions. But some people don't like this because the model that you're launching into production, you don't actually have an apples to apples measurement of how things are going to go. You have trained data only model and train validation test data put into a new training set and rebuilt model. And so these are technically two different models, same parameters, same model structure, probably gonna perform similar, but they're not exactly the same. And so uh, you know, some people will choose, okay, I'll take my training data, my validation data, put them together, rebuild my model, and that way I can use my test statistics. My boss doesn't like the refitting idea. I like the refitting idea. By default, the Carrot package refits using train and validation data put together if you go in and you read the help documentation on that. And so here, what I've presented so far is don't refit the model. So the model that you use on the train data is all you're going to, that's it. This goes into production. Now, after I've selected my best validation model, another option would be to combine training and validation data, rebuild the model, and then I do my test statistics. And then another one, after I do my train validation and test statistics, I go and I recombine all the data into one, rebuild the model. And so here I'm using all my data, but I'm really, comparatively, I'm flying blind-ish with that model. Do whatever you feel is best. In the Carrot package, if I want to control this a little bit, I get more nuance, we can do index final parameter and index in, index out for controlling this aspect. All right, now, sometimes we're actually going to put observations in our training, validation, and test data. We don't want to do that. In our partitions, we want to be exactly that, a partition. Each data point is in one of 3 data sets, and there is no overlap whatsoever. But imagine a situation that I have imbalanced data. Let's say that there's a really, really rare event going on, and that's my target variable. Well, if it's super, super rare, I might have to go ahead and put it in all 3, put my target, like the positive cases, into all 3 data sets because my data is so imbalanced. It's possible that like maybe I have an underrepresented population and I'll go ahead and put them in multiple spots. If I choose to do that, I have to know that all of my statistics are going to be optimistic, especially when it relates to like precision, recall, things like that. It's an option. We should avoid it, but sometimes it's the best course of action. All right, so now I want to talk about ways to select our training and validation data. First one is the holdout data. So here I randomly pick training, I randomly pick validation, I randomly pick test. And that's how it goes. And that will be my training, validation, and test data. And so here, we just set it up and we control how things are going to go. So to do this, we have, or it's index, it says index in a moment ago incorrectly. I use index as my train data. I use index out as my validation data. And so here's my holdout set. My test set, you'll notice is not even part of the Carrot package function call. And so here we get our, our validation statistics. Now, another way that we can choose our train and validation data is by bootstrap. And so, we sample with replacement, number of observations equal to the total observations I have in my data set. And so here, the data that's not selected for the training data, so the bootstrap selects the training data, everything else is selected as my validation data. And that's how this is the default setting for the caret package for the train function. And so, but if I want to call it explicitly, I put it into the train control function of the train control parameter, and method equals boot for bootstrap, and we can get our result. Now, k-fold cross-validation, here what we're going to do, I'm going to chop up my training and validation data into subsets. And so let's say I'm going to just use 3 because 3 is the easiest to explain. I'm going to break up my train and validation data, which is in one pot, one group, into 3 subsets. I'm going to build a model where this set is validation, these 2 are trained. I'm going to build a model where this data is validation, these 2 are trained. I'm going to build a model where this data is validation, these 2 are the training data. And that's our cross-validation. And so this gives us like a distribution of values. And so in this situation, I would have 3 validation statistics, and I would have 3 training statistics for my model. And so this gives me a more complete view of how my model will perform in the future. Typically, cross-validation is done with 5 or 10 folds, and fold refers to like each of the splits of the data. 10, I feel like 10 is the better one because you get a better view of the distribution off of that. So here, we can get our results. Now, repeated cross-validation, this one I like a lot. And so here, what I'm going to do cross-validation, but then I'm going to randomly split my data again and do cross-validation. I'm going to randomly split my data again, do cross-validation. I'm going to do this repeatedly. And so I like to use this with 2 folds. We use 2 folds. In that situation, I've got train validation, and then I have train validation. They switch roles. I build 2 models instead of like 10. All right, so that's relatively fast. If I'm doing 10-fold cross-validation, I'm using 90% of my train validation data. With 2-fold cross-validation, I'm using 50%. So if time is an issue, 2-fold is going to be fast comparatively. And so but I'm only getting like 2 numbers off of it, off of each run. And so you know what? I can do this repeatedly. If I do it 10 times, I'll end up getting 20 data points off of this. And so I can get a more complete view, and individual models will be computed faster. And you'll find with a lot of model structures, when I have a lot of data, it'll take longer this way than if I was building models and, by counting the number of observations being plugged into the training rounds, this will actually be faster than like 10-fold cross-validation one time. Now leave one out, cross-validation. Okay, so this is cross-validation within folds. So if I had 1,000,000 data points, leave one out, cross-validation would be doing 1,000,000 folds. Each observation at one point is the validation data, and every other data point is the training data. And so this is computationally expensive. This takes a long time. This is a good choice when I have very little data. Now, there is a catch to this that is kind of nice. For linear regression, there is actually a special formula that makes this instantaneously fast. And so if I'm doing standard linear regression, there's a special formula. Don't do it the caret package way. Don't use the scikit scikit-learn way. Don't go straight to like base R or stat models for it. All right, so there is large group 1 cycle validation. This is another choice we have. And so this is creating one large random split of the data into training and test set used for a single cycle of model training and validation. That's a typo. I should have validation. I should have validation here. And another option we have is none. Generally not recommended unless I'm in that small data situation, but it's an option. That here I'm just doing everything into training, or I'm doing train test split, but no validation data. Now, another option I have if I'm doing a bagging model such as random forest is to use the out of bag situation. So remember, we're doing that bootstrap thing, and now on each individual submodel in a random forest, we do a bootstrap selection of our data. Well, the out of bag are everything that's not selected by the bootstrap sample. And here we use those as the validation data. My experience is that out of bag statistics tend to be optimistic, but not as optimistic as the training data. But it's a good choice if I have light data going on. A lot of random forest models will actually compute this automatically for you. Now here is a modified version of the Bootstrap algorithm, and so this, is a composite estimate of performance that weighs the training and Bootstrap validation performance, and that's Boot 632. There's Optimism Boot, which is another modification of the Bootstrap. And so here it compares the performance on the Bootstrap sample with the whole data set. And there's also adaptive models. And so here, adaptive resampling methods like adaptive k-fold cross-validation, adaptive bootstrap, and adaptive LGOCV involve conducting futility analysis during resampling. And so models with low chance of being optimal are eliminated early on so that we just don't waste our time. And so I ran through the 3 that are in the carrot package. All right, so we've talked about our validation data extensively. All those different algorithms are all about the validation data. So now, what about our test data? All right, so there are a couple of different ways that we usually pick our test data. Random selection, which is what I did at the beginning of the video. Time-based selection, so this is the one that for a project that I'm closing out right now, we picked the last 6 months of our data to be our test data. And so that's the time-based selection. This is especially, this is used a lot, especially for the situations like time series. And then it's also possible that there's a data set, a subpopulation of data that's super, super important. And I'm going to make sure that that important data set is selected in my test set. All right, so for your homework, go through and just try different partition techniques that I showed above. Do a holdout set, do no holdout, do bootstrap, do adaptive cross-validation, repeated cross-validation, mix it up, see what works for you, see what you like, and submit your results. All right, well, that's all I've got for you. Life is short. Do math.